Hello everyone, my name is Łukasz Bratasz. I'm head of the Cultural Heritage Research Group, which developed HERIe preventive conservation platform for decision support. And today I'd like to speak about the mechanical damage module, which is by far the most complex module which we have developed and implemented on the HERIe website. It's complex both in terms of the number of lines of the code, also the complexity of the mechanical model in itself, and also some issues with the not obvious interpretation of the results which you can obtain using the module. Frequently, I'm asked by the friends, by colleagues, by the users of the HERIe software to give more friendly presentation, background information, how the module works, more friendly comparing to the information which is already in the HERIe under the button manual and mechanical damage tool. And I plan this presentation, this video to be more friendly, but also I want it to be a little bit broader to give the more background information about the mechanical risk due to the environmental variation in general. And I would like also to illustrate the risk of the mechanical damage with these beautiful objects, the Mazarin chess from the collection of the Victoria and Albert Museum, which is the wooden object decorated with the Japanese lacquer. And here you can see that in the lid there is a crack going between the planks here and the frame here. And generally, the mechanical damage in objects due to interaction with non-stable environment, fluctuating environment, is due to the various dimensional response to relative humidity or less frequently to temperature. And this happens mainly to the materials which are hygroscopic. It means that they absorb moisture when relative humidity changes. And here you can see the data obtained for the limewood. Here you can see the change of the mass versus relative humidity. So when you increase the relative humidity, mass object increases as well, and it increases following this line which we called absorption branch. And when we start to decrease the relative humidity, it returns through the different path which is called the sorption path. And this loop here is called the sorption hysteresis. And when objects, materials absorb moisture, they also change the dimensions. So here you can see the results which we measure for around 25 wood species in the tangential direction. And as you can see here, the data are quite scattered, but more or less the expansion, the dimensional change of the wood in tangential direction is around 5% when changing relative humidity from 0 to 100%. And as you can see here, we selected the limewood as it is quite typical, both in terms of the maximum sorption, or it is rather not typical, it is also expanding a lot material, and above 50% also expansion coefficients are higher than other type of the woods. Probably you also know that wood is orthotropic material, so it has different material properties in the three anatomical directions. And here you can see the swelling. So this is the swelling is the dimensional change from the dry condition in the tangential, radial, and longitudinal direction. As you can see here, the dimensional response is most pronounced in the tangential direction. The response in the swelling in the radial direction is more or less half of the value for the tangential direction, and wood is, from the practical point of view, stable in longitudinal dimension. So we know that wood responds to humidity variation by sorption and then by dimensional changes, and we call this relative dimensional change strain. Strain is the total strain is the change of the dimensions comparing to the initial dimensions, and it equals to the strain which is caused by the humidity variation, and we need to add to that the strain which is caused by the forces. So the equation is that the total strain, as you can see, equals the beta, which is moisture expansion coefficient, multiplied by the change in relative humidity, plus elasticity modulus for the material, multiplied by the stress applied to the material. The important part is, of course, strains, which are caused by the stresses, because it can lead to the damage of the material. Here you can see typical stress-strain curve for the limewood again. On the y-axis we have stress, which is generated when applying the strain, when stretching the wooden sample. And when the strain is relatively small, we can see that there is a linear behavior above the yield point. There is a deviation from the linear behavior, which means that there irreversible deformation, plastic deformation happens in the material, and when material reaches the strain at break or the strength of the material, there is a failure and material cracks. So let's return here to this equation, and we can see here that if there is no restraint to the movement, the object is, or material, the wood is free to respond to relative humidity variation. The moisture strain or HERIe strain is equal to the total strain, and the elastic strain is 0. But if we restrain the wood, so when we block it in the deformation, so the total strain is 0, so the HERIe strain plus elastic strain equals 0. It means that the moisture strains generates the elastic stresses, so the stresses which are responsible for the damage of the material. One can ask how it happens that without external force applied to the object, we reach the stresses which can break the wood or the material. And Marion Mecklenburg convincingly showed that the same stresses can be achieved by applying the external load or by changing relative humidity. And let's imagine that let's consider this situation that we have object at certain relative humidity. We extend the sample by external force, so the stress reaches this point. And you can reach the same point of the stress, the same level of the stress going through the different path. So let's imagine that we have the wood, we change relative humidity, so it reaches the dimension L1, and then we block the wood in a movement, we restrain it, then we lower relative humidity, and the stresses increases and reaches the same level. So applying the external load and changing relative humidity and restraining the material in the movement can produce the same stresses. In fact, they are equivalent. So returning to our Mazarin chess, we can see here, and we can ask the question, what is the restraint in this case? So here you can see the construction of the chess and the lead, and here there is a plank cut in the radial direction, and there is a frame of hinoki wood cut in the longitudinal direction. If you consider that wood is much more stiffer in longitudinal direction, more or less 20 times more stiffer than in radial and 40 times stiffer than in tangential direction, so you can see that this direction is much more stiffer and restrains the plank from the wood movement. So when changing relative humidity, the plank is responding much more in this direction, in radial direction, than in longitudinal, but longitudinal direction restrains its movement, and the stresses appears at the borderline and in the plank. And in fact, the crack was created in this area. So the source of the restraint, sorry, something that the source of the restraint could be or external construction or internal construction of the wood, but it could be also caused by the various dimensional response of the wooden support to the pictorial level, and it can cause the cracking of the pictorial level. So the question is how to determine acceptable climate variability, and there are three approaches to answer this question. The one is understanding of the mechanical behavior of the objects in response to climate variation, and we use typical approaches as engineers use to evaluate, for example, maximal load of the bridge. We can use acclimatization concept, which says that if you stay within the range of the past humidity variation or temperature and humidity variation, the risk of the further damage development is negligible. And thirdly, we can use non-destructive methods of tracing damage development directly. And with this method, using these techniques, we can observe actual rate of damage development in the object and correlate it with the environment. I will not speak about the acclimatization and non-destructive methods. I will just focus your attention on mechanical behavior. And this is quite problematic, how to evaluate, how to determine what is safe and what is not safe for the objects, because we have thousands of objects in the collections, if not millions. We don't know the material properties, we don't know the precise construction, we don't know the environmental history. So Marion Mecklenburg proposed the approach which we call the worst case approach, in which we define the most vulnerable to humidity variation virtual object. In this case, this virtual object is defined by the largest differential dimensional response in the adjacent layers compared to the yield point, to the criterion of damage. And in this case, it is wood in tangential direction and animal glue-based ground, which we called also gesso. Here you can see the several materials and the thermal expansion coefficients. In the second column, and in the third column you can see moisture coefficients of expansion at 50% relative humidity. And what you can see here, the largest difference in dimensional response is between the wood in tangential direction and the gesso, which has the lowest dimensional response. If you combine this with the information that gesso at lower relative humidity is very brittle material, it cracks very easily, and the critical strain is only 0.002, then you have the worst case scenario. The combination of the wood and the gesso at lower relative humidity is the worst case. Of course, gesso at higher relative humidity can be extended, can be stretched significantly without cracking, but still the yield point, the point beyond which the irreversible plastic deformation starts, is more or less the same, and we assume the 0.02. So let's use this information to evaluate the climate. For example, here you can see the relative humidity variation in the one of the gallery of the National Museum in Krakow. And we can interpret the environmental guidelines of IIC, ICOM-CC 40-60% as a plus minus 10 around the long-term average level of relative humidity. And in the case of the National Museum in Krakow, this was 45%. But still you can observe that there are some periods in which the relative humidity drops below 35%, and the question is, are they safe, or otherwise are they dangerous? Are they risky to bring the risk to the objects? And let's use this object as a kind of the indicator of the risk, which is the 15th century tempera painting on 10 millimeter wooden panel varnished from one side from the collection of the National Museum in Krakow. And let's look at the dimensional change, the strain of this object, which is much better indicator of the risk than just relative humidity variation. To do that, we built model in one of the available software for finite element modeling. In this case, we use the COMSOL multiphysics software. And here you can see the example of such model. And moisture can access the object only from the back side because the front side is varnished. And there are three distinct steps in the modeling, and each of them I will try to explain. So we upload the environmental data, and for which time instant we read out temperature and relative humidity. For that, we calculate the moisture transport, and here you can see the diffusion. We need to have the information about the diffusion coefficients, and for example, we use the diffusion coefficient proposed by Thieme in 1998, which more or less corresponds to other values. We use also information about external mass coefficient, and then we calculate the information about the moisture sorption using information about the absorption and desorption branches, and we do that both for the wood and for the gesso layer. In the third step, we refine the information in the model about the mechanical parameters, mechanical properties of the material. For example, here you can see the dependence of the elasticity modulus of the wood in radial and tangential direction as a function of relative humidity, and also information about the stress strain curves for the gesso layer. Then we need to calculate what is the mechanical response, what is the dimensional response, and we use all information about the swelling isotherms for the wood in tangential radial direction, as well as the swelling isotherms for the gesso. This graph, in fact, shows the stress strain curves determined for the gesso when we apply the strain, and for various relative humidity, and the distance between these points corresponds to the dimensional change of the gesso when changing relative humidity from 23 to 40% of relative humidity. And finally, having all this information, we calculate the local strains both in the wood and the gesso. And to say what is safe, what is not safe, we need to compare them with the damage criterions. And as I mentioned, for the gesso, we use damage criterion 0.002, and for the wood, usually we use the criterion as a yield point 0.05 and as a strain at break 0.2. So, as I try to explain, the Marian Mecklenburg proposed his worst case scenario when we look only on the dimensional difference in dimensional responses on the failure criterion, but in fact the finite element modeling allows for more precise determination what is safe, what is not safe, and in fact several phenomena are taken into account. For example, hysteresis in the swelling and shrinkage. Here you can see here, for example, how the moisture content changes with the relative humidity. As I said, you have the absorption branch and desorption branch, and when you start from the medium level and middle level of a range, 50%, and you go to high relative humidities, the moisture content approaches slowly the absorption branch. When you lower relative humidity, it approaches the desorption branch. What is important that the slope of this curve is smaller here. We call it scanning isotherm. The slope of the scanning isotherm is lower than the slope of the absorption or the desorption branch. So it broadens the safe range of humidity variation. Another effect is that objects are not responding immediately to humidity variation, and they have usually slow response, and it can take, depending on the thickness of the type of the diffusion, from hours to days or even months or sometimes a year. Here you can, in this graph, you can see the thickness of the panel, here the response time, and we calculate this response time as a function of temperature. The blue lines shows the response time for the 7 Celsius degrees, and the red lines shows the response time for 25 Celsius degrees, and we consider again two situations. One is then when we have symmetric diffusion from the both sides, so the face and the back are diffusively open to the moisture, or we can have the asymmetric diffusion when one side is blocked, usually the front side with the oil paint, varnish, or gilding. And as you can see here, that, for example, for 20 millimeter thick wooden panel, the response time when diffusion is asymmetric, the response time is around a week. But when we lower temperature to 77 Celsius degrees, the response time is around 9 months. This is considerable effect of the lowering temperature. Just lower temperature slows down moisture diffusion. And another effect, which also broadens the range of the humidity variation, comparing to the worst case scenario proposed by the Marion Mecklenburg, is ability of the panels to deform, and the finite element models softwares allows to do that very, very efficiently. We always check the quality of the simulation we always validate the simulation by comparison with the experimental results. And here you can see the wooden panel covered with the gesso layer exposed in one of the gallery of the National Museum in Krakow, and we monitor both relative humidity, temperatures. You can see here relative humidity, you can see here temperature, and the black curves represents the measured deformation of the objects, and the green curve shows the simulation. And more or less you can see that simulation mimics the actual experimentally measured values. So let's return to our question, is this climate safe for the object? Is it acceptable for the object or not? And I have shown how to build the model, what are the basic steps in the modeling, and let's look at the results now. So here you can see the strains, which are compared with the gesso-crit strain at failure at lower relative humidity, or yield point, which are our critical values. And you can see that strains which are experienced by the gesso layer caused by this unstable environment do not reach the critical values. The numerical simulations of strains histories are a very efficient way to evaluate the environment and assess the risk and determine safe range of the humidity variations, but they have a few drawbacks. First of all, they are time-consuming, require large computational power, and specialized expertise in program. So not all museums, or I would say the contrary, very few museums has resources to perform this kind of the modeling. Therefore, we proposed alternative approach, which is based on the decomposition of the real climate into elementary sinusoidal array variations using fast Fourier transformation. Then elementary strains variation are calculated and collected in the database. And finally, elementary strains variation corresponding to the environment, to the climate, are fused against into complete object response, and that's available on the HERIe platform in the mechanical module. So in the first step, the composition of the array variation takes place, as I mentioned, using fast Fourier transformation. Here you can see the example of the environment. And as you can see here, there are quartile variation, but the yearly average variation is 45 degrees, percent. We decompose it into we break down to elementary sinusoidal variations, which are characterized by the amplitude, by the period, and the phase shift. But the Fourier transformation gives us also information about the average RH level. But because the response time of the object could be shorter than in 1 year, then the objects adapt to the new level of humidity variation. It is why the Fourier transformation is performed in the windows corresponding to the response time of each individual object. And this window moves, and we perform the Fourier transformation in each window separately. Then relative humidity variation are translated to the strains cosine using finite element modeling, and we perform this modeling for the two types of the object. One is freely responding panel covered with the gesso layer, and the second is restrained wooden panel, for example, doors, size of the cabinets, and etc. And here you can see how it looks like. So we have elementary RH variation, and we calculate elementary strain variation. But it's important to know where to calculate the strain variation. For the restrained wood case, we calculate the strain as an average of local strains across the wooden panel. And in the case of the panel painting, we calculate strains in the gesso layer at the interface between the gesso and the wood. Why it is so? Because the strains at the interface, they are the largest. Here you can see the sinusoidal RH variation, just an example, and here you can see the local strains experienced or by the gesso or by the wood. So this graph corresponds to the point of the maximum RH, which in this case is 55%. And as you can see here, there is a slight distribution of the strains, but the strains are the largest at the interface in the gesso layer close to the wooden substrate. And when the relative humidity drops to the minimum value, we have the reverse situation, but again, the strains are the largest at close to the interface between gesso and the wood. Here you can see one of the results of such simulations. The blue line represents the relative humidity variation. The black line represents simulated strains in the object, and the green curve is the cosine function fitted to this obtained variation, and in this way we can determine both the amplitude of the cosine variation, we can calculate additional time shift, and also we can determine the change of the zero level of the strain variation. As you can see here, the strain is a little bit shifted up. Why it is so? There are two reasons for that. The one is that moisture absorption curve is a little bit higher at higher relative humidity, so wood absorbs more at the same change of relative humidity variation, and also the diffusion coefficient at high relative humidity is faster, is larger than at lower relative humidity. So it means that when we increase the moisture, the wood absorbs more than it desorbs during the period of the lower relative humidity variation. It is why we observe this slight shift. And we performed this calculation, we calculated the cosines strains for the various amplitude of the range variation, starting from very small and ending on 20%. We calculate for different periods, starting from hours and going to many days, more than 1 year. We also have a different levels of humidity variation, starting from 25 going to 30, 35, and the highest average relative humidity at which the humidity changes is 75%. We consider 4 panel thicknesses from 5 to 40 millimeters for temperature 7, 15, 21, and 25. We also consider two moisture uptake configuration through the one phase and through the two phases in a panel. We calculated it for the four wood species: lime wood, which is typical for the Central Europe; poplar, typical for the Italy; oak for the Western Europe; and pine, typical for the Scandinavia. Two orientation of the wood grains were considered, tangential and radial. We consider also two gessos, one stiff and one soft. And we, of course, as already mentioned, we calculated it for the panel painting and for the restrained wood. And usually, and we use the linear interpolation to find the values which fall between the calculated strains. So as you can see here, there was quite a lot of calculations. The database is very large, but it allows us to pull all information back without waiting for the long time for the full finite element modeling. So when we have this database, we have the decomposed relative humidity variation, then we can fuse the individual strain cosines into full strain versus time history at 50% of relative humidity. Additionally, strains are adjusted to the average level in each time window, and we need to make assumption where is the zero stress strain level. And usually assume that this is a default solution, that is zero strain level is at average array level of the data which were uploaded, but the user has also the choice, it can select a different level. At the end of this presentation, I would like to mention about the limitations and the problems of the HERIe platform, particularly about the problems of the mechanical module. And the main is that panel painting module doesn't work properly above 75% of relative humidity, because above this level gesso softens significantly, and we cannot use the superposition rule to reconstruct complete strain versus time history from individual elementary strains. Also for the teak wood and teak panel paintings, and particularly at lower temperatures, we experience numerical problems at the beginning and at the end of the calculation, and this is caused by the fast Fourier transformation, which requires periodic data. Because we have only limited set of data, we need to reconstruct it in the past and in the future, and this doesn't work still properly, but we are working on that on the new protocol, and we will fix it in future. And now at the end, I would like to say a few words about the interpretation of the results. And as you have heard during this presentation, the HERIe mechanical module is based on the worst case approach, which overestimates the risk of mechanical damage. So because this is very nature of the worst case approach, we are assuming that our object doesn't have any initial damage, and we use the damage initiation as a criterion for damage, whereas the objects adapted to the unstable environment in which they were stored for the long time have a lot of cracks and damages, as you can see here. And for such objects, the damage propagation should be used as a criterion, but we don't have such tools yet, or we as a heritage field, but we are also working on that. The good thing is that the worst case scenario, when it determines that some variations are safe, they are probably more safer than the tool shows in itself. And at this point, I would like to thank you to the institutions and agencies which support the development of the HERIe software. Thank you very much for your attention.